This is the AB 61263 review, number 7, and this time calculators are allowed. So the tough part is going to be just setting this up, and then you can just enter it into your calculator and call it good. So on this one, we want volumes of solids, and it looks like we've got cross sections that are specified shapes. So on part A, the base of the solid is a region enclosed by the coordinate axes and a parabola that opens up that has been moved 3 units to the right, and cross sections perpendicular to the x-axis are equilateral triangles. So first thing we're going to do is draw the picture. We've moved 3 units to the right, we're opening up, and we are doing the region bounded by the coordinate axes and the curve. So we've got an intersection of 3, 0, 0, 0, and 0. If I plug a 0 in, that's a 9 squared, or excuse me, a 3 squared is a 9 times 2 is an 18. So obviously not drawn to scale or proportional, but we can still work with it. And the cross section is a perpendicular to the x-axis. So this will be x and the function. And this one will be x and 0. Now off of that strip, which is vertical, we're going to build an equilateral triangle that has a hair of width. So the width is a dx. The length of that strip is the top y coordinate minus the bottom y coordinate. And the height is half of that length times a root 3. So we'll lose the 2 because we take half of it. I have a root 3 times that x minus 3 squared. So now our job is to set up the volume of that slice. Well, it's got a face that's a triangle, so that'll be a 1/2, a base times a height times a thickness, and then we'll add them all up. So adding them up, we have a vertical strip, so that means we're in terms of x, so we need the lowest x value and the highest x value. So we'll be accumulating from 0 to 3. So before I put this in my calculator, I am going to collect all of the constants. So the 1/2 and the 2 will cancel. I have a root 3 out in front. And then it looks like I have 2 of these, so that's an x minus 3 to the 4th. So if I multiply that out, I will end up with a 243 root 3 over 5. And I'm going to assume that you can put that into your calculator and get the answer out. So let's look at part B now. Part B says the base of the solid is a circle of radius A. So we've got some A's in here, which make it a little challenging. And every plane section perpendicular to a diameter is a square. So we're going to get to pick which diameter we use. Chances are this is going to be the easiest to set up if we put our curve as a circle centered at the origin. So we've got an x squared plus a y squared equals an a squared. And let's cut with respect to x. So we're perpendicular to the diameter lying across the x-axis. That makes it a little simpler for us. So we can now label in terms of x. And the y's will be if we isolate y on here. So that's going to be a negative root a squared minus x squared, and this one will be a positive root a squared minus x squared. So now off of that shape, I'm going to build a square. And that square will have a hair of thickness that is dx. And the length of it will be this top y coordinate minus this, which actually gives me 2 of those roots. So if I want the volume now, it will be the area of the front, which is this, times the same thing since it's a square, so that'll give me 4 of the root times the root, that's an a squared minus an x squared without a root, times the thickness, and I'm accumulating from negative a to positive a. Since my diameter, or excuse me, my radius was an a, I'll go out to negative a and forward to positive a. Now the issue is I don't like working with negatives, so I'm going to double the accumulation going just from 0 to a. Because of the symmetry, I can do that. So looking at this, I've got a constant that I can pull out. Sorry, that'll give me an 8 accumulated from 0 to a of an a squared minus an x squared dx. So now we need to answer the question, what did I take the derivative of with respect to x that gave me this inside? And remember that a is a constant, so I'll have an 8 times an a squared x minus an x cubed over 3. And I'm going to evaluate from 0 to a. Now what's fortunate is if I evaluate the 0, I get nothing. So really I just need to plug in the a. I'll have an 8 times an a cubed minus an a cubed over 3. So if I get a common denominator, I have 3 of those a cubes over 3 minus 1 of those a cubes over 3 gives me 2 of those a cubes over 3. And then I multiply by 8, gives me a 16 a cubes over 3. Didn't need to use a calculator for that one. Alright, so let's look at part C, last one. The base of the solid is bounded by a parabola, a horizontal line, and plane sections perpendicular to the y-axis this time are semicircles. So we will start by graphing. We got a parabola, and that one opens sideways. So let me move my axis here. It's a sideways parabola, and it opens to the right, and its vertex is at 0, 0. And then we have the horizontal line y equals 2, bounded by the parabola and the line. I'm assuming, oh, you know what? That is not a parabola open sideways. I saw the x and just made an assumption. So, bad picture. We've got x is still squared. So if I isolate my y, which is a thing that's not squared, I actually get a parabola that opens up, and it's pretty fat. So let's redo that. We got this fat parabola and a horizontal line y equals 2. So when is this going to equal 2? That's when x is plus or minus 4. And we're supposed to cut perpendicular to the y-axis. So this point here is going to have y as a coordinate, and this point here is going to have y as a y-coordinate, and the x-coordinates are going to come from isolating x. So this one will be a positive root 8y, and this one over here will be a negative root 8y. So if we build a semicircle off of that strip, we are going to have a hair of thickness that's dy. The length of that is going to be a root 8y minus another root 8y, which is 2 of those root 8y's. And we need to write the volume of that semicircle. So that's going to be a 1/2 pi times the radius squared dy, and we'll sum them all up. So the radius is going to be half of that diameter, so that's just going to be your root 8y, and the y's are going to go from 0 up to 2. So if I multiply this out, I get a 1/2 pi integral from 0 to 2, square the root, I get an 8y. Move that 8 out in front, I'll get a 4 pi times the integral from 0 to 2 of just a regular y. So what do I take the derivative of with respect to y that gives me a y? Well, that's a y squared over a 2. Plug in the 2, I get a 4 over 2, which is a 2 times 4 gives me an 8 pi. Plug in the 0, I get nothing, so I end up with 8 pi.